Next, principle of moments. For example, I have, let's consider seesaw. Okay, so on this seesaw, here is the point. This will be where it is balanced. This will be called as fulcrum. And if already some weight is there, then this will be called as load. So to lift the load, what we are going to put? We are going to do some effort. Okay, so mechanical advantage. This is mechanical thing. So mechanical advantage equal to load by effort. Okay, mechanical advantage is nothing but load by effort. Load is nothing but force, effort is also nothing but force. So both the units Newton. So mechanical advantage have no units, right? So now let's consider some different thing. Now it's just mass. Now same here is some fulcrum. So some force is acting at this point, some force is acting at this point. This is at a distance of d1, this is at a distance of d2. Okay, now here let's consider this force is F1, this force is F2. Okay, so this system is not going to anywhere, it is in rest. That means two forces are acting downwards, but even though it's not coming down, that means there is some force is acting upwards, some force is acting upwards. That force will be called as normal force. So that normal force will be equal to downward force, upward force will be equal to downward force, so that we can say it is in translational equilibrium. What about rotational equilibrium? Rotation means torque should be torque should be zero. Rotational equilibrium la torque should be zero. In translational equilibrium, uh, force will be zero. Okay, so now in rotational equilibrium, torque will be zero. Torque will be zero means this side and this side will be equal. So this side torque, that is F1 into d1. This side is F2 into d2. Then both will be equal. Okay, clear? Then F1 d1 equal to F2 d2. Clear? Right. So this is about simple rotational equilibrium. It is in translational equilibrium. Okay, this is only called as principle of moments. Okay, clear? Understand? If distance is increases, if distance is increases, the applied force will be less. Okay, fd1, if d1 increases, f1 will be decreases, so that force will be, torque will be there. Okay, clear? Torque will be constant. Got it? So if distance increases, less force need to be applied. That's all. If the force will be less, then you need to apply, if the distance will be less, you need to apply more amount of force. So by using this one, we are about to find the problems also. Okay, let's see it. Let's consider there is one meter scale. Meter scale means what is the total length? 100 centimeters. Let's consider at a distance of 40 centimeters from the starting. At the center 40 centimeters, there is a fulcrum which supports. Okay, so that here it is balanced. It is balanced when here they kept 1 kg mass, 1 kg mass at a distance of 10 centimeters, at a distance of 10 centimeters. So that they are asking what is the total mass, what is the total mass of the scale. So this is at a distance of 40 centimeters. That means torque is going to happen from this point only, no? So this is the origin point. So what is the distance? What is this distance? This distance is, this is 40, this is 10, so it will be 30. So torque 1, this torque is how much? How much? 1 kg. 1 kg means, I mean mg, force mg into distance of 10 centimeters. Okay, let it be in centimeters, no need of conversion. As I am not taking, this is okay, here mass 1 kg taken, no, so it should be converted. Fine. So T1 equal to mg into 10 centimeters, 30 centimeters here, 30. So 30 means 30 into 10 power minus 2. That means simply T1 equal to 0.3 mg. Here mass is how much? 1. So tau equal to 0.3 g. Okay, tau equal to 0.3 g. Now this side, total mass. Total mass is m. Okay, I don't know total, I want to find the total mass. So for this total mass, where is the center? Weight is acting from the center, that is at a distance of 50 centimeters. 50 centimeters, initially 50 centimeters. After keeping this, a fulcrum has come here to balance it. So this is 40, then what will be this distance? This is also 10 centimeters. Okay, now mg. So now torque T2 equal to this total mg is the force into what is the distance, at what distance it's happening, 10 centimeters. That means 10 into 10 power minus 2. So T2 equal to this total mass, don't know, gravity, let it be g into 0.1. So what is the total net torque? Net torque is equal to 0. Okay, so torque tau equal to tau 1 plus tau 2. Torque total tau equal to 0, then it will be tau 1 plus tau 2. So tau 1 equal to minus tau 2. First torque equal to second torque. Okay, so that means first torque will be equal to the second torque. So 0.3 g equal to capital mg into 0.1. So g gets cancelled, 0.1 sir, 0.3 sir. So mass equal to, mass is how much? Mass equal to 3 grams or kgs? Kgs. So total mass is 3 kgs. Okay, next, couple of moment. So couple or couple of moment. So couple means not only boy and girl. Okay, so couple of moment means two forces. Okay, so what are the two forces? Let's consider one object, rigid bodies. All will be considered as rigid bodies only. Okay, from particular point, from this particular point, let's consider from this particular point. Here I am applying a force in this direction, F, at a distance of R1. Now I applied a force in this, at this point, at a distance R2, but in opposite direction. Then these forces are said to be couple. Okay, but how the forces are acting in opposite direction? So both are magnitude wise equal, but are in opposite direction. That means this is the line of action of force, this is the line of action of force. So this will be the center point where we will consider as axis of rotation. Okay, clear it, right? So this will be, because of this what will be happen, this is going to rotate in this direction, because of this it's going to rotate in this direction. So it is anti-clockwise, clockwise. Same what we done before, torque equal to tau 1 plus tau 2. Okay, both will be taken and both will be solved. So you will get torque equal to r1 bar minus r2 bar into f bar. Okay, this is the torque. Got it? Right. So this is called as, this moment of given couple at any point is constant. Okay, about any point this couple will be constant, this forces remains constant. Okay, right. Next, mechanical equilibrium. Mechanical equilibrium. So what is meant by mechanical equilibrium? If a body has both translational equilibrium and rotational equilibrium, then we can say that is in mechanical equilibrium. In translational equilibrium, which is constant, velocity is constant. Okay, in velocity constant, that means force will be 0. In rotational equilibrium, angular velocity is about to constant, so torque will be 0. So that means sum of force will be 0, sum of torque will be 0. Okay, that means here there is change in momentum, dp by dt is 0. Okay, dp by dt, change in momentum is 0, but p is constant as velocity is constant. Okay, in case of angular momentum, so here angular velocity. Okay, that means angular momentum dl by dt, angular momentum. Okay, this is the angular velocity, this will be angular momentum. Angular momentum is 0, but angular momentum is constant. Change in angular momentum is 0, but angular momentum is constant. So in rotational equilibrium, the angular momentum of a body is constant, and this rotational equilibrium is independent of location of origin. Independent of location of origin. Wherever you will consider, there will be wherever you are considering about torque. For example, from this point, where you are considering at this point, at this point, at this point, any point you can consider regarding torque. From the torque will be produced from this point, or from this point, from this point, or from this point, any point. This rotational equilibrium is constant and it is independent of it. Okay, it does not depends on it. Okay, clear? Right.